Swayam Prabha. Digital India. Educated India.
In the last class, we had developed the stress field equations, and particularly we saw the stress field in the very near vicinity of the crack tip. We have seen the solution by Westergaard. We also saw certain modifications on the Westergaard solution, and one of the important modifications you have on Westergaard's equations is the modification by Irwin. In fact, while interpreting the results of Wells and Post, he added an extra term, and this is to essentially the sigma x stress term, you have a quantity minus sigma naught x. Although the final objective may be to find out K1 from the experiment, you will have to use the experimental information to find out sigma naught x as well as K1, and then report the value of K. Only that value of K is representative of the actual stress field seen in an experiment. This is the way you will have to look at it. And we have also seen the kind of fringe patterns that you get by using this stress field equation. We will have a look at them again. We have calculated the maximum shear stress along the crack axis, turns out to be a constant value. This is the generic expression. When you plot these, you had fringe patterns like this, and when we compare it with the experimental fringe patterns, it matched quite well. And this is what I said, a simple modification by Irwin has helped you to capture even the tilt of the fringes. This is becoming straight, which was inclined like this, tilt of the fringes was inclined like this, and it is becoming straight as you go close to the crack tip, and that is what you see in the fringe patterns. But along the crack axis, it also gave only a constant value of the maximum shear stress, whereas in the experiment, even in this case there is a subtle variation. You could see prominent variation in problems where the crack is long or where the crack is situated in a stress concentration field. In addition to this, we also saw what are the modifications done by Tada, Paris and Irwin. What they looked at was, they looked at, while shifting the origin, we had made a simplification. Instead of simplifying the way that we had done, you could express the denominator as a binomial series. So, you essentially get a series solution, and if you look at whether it has helped in satisfying what is seen in the experiment, if you really look at, it has not done so. Though it is not shown here, along the crack axis it predicts no fringe order, very similar to the original Westergaard equation. Though this modification was tried, this modification was not useful. When you have serious terms, you normally think, okay, if I take the first term, the solution is to a certain level of accuracy. If I take several other terms, the accuracy keeps on increasing. That kind of a generalization you cannot make it here. The first term is still what you have in your conventional Westergaard solution. Now, what we will do is, we will also have a look at some aspects of the basic solution by Westergaard. Let us see what all we understand from the basic solution here. I have what is known as a stress intensity factor, and there is a function of r and theta that is given. As the loading is changed, you would find the value of K1 changes. The value of K1 really determines the strength of the stress field. Suppose I have multiple loads which are giving you a mode 1 situation, then from principle of superposition you can add the K1s for different types of loading. And what happens when R is close to 0? The values asymptotically increase to infinity. In a real material it cannot go to infinity, it can only reach a value dictated by the material behavior. It may be, if it is a perfectly plastic material, it may reach the yield strength. If it is a work hardening material, because of work hardening it will reach some other value of stress level. This is what would happen exactly at the crack tip. How small or how big this zone is problem dependent. Another aspect what we looked at was this solution is actually valid very close to the crack tip, because we had made a simplification, z naught is much less than a, and that is how you have got. Suppose you look at this, when R tends to infinity, what happens to the stress values? They essentially go to 0. So, you are only capturing the stress field very close to the crack tip. And what was the modification done by Irwin? He simply added one extra term. And I had mentioned earlier that you need this to interpret the experimental fringe pattern. Though your interest may be to find out only K, you process the data from experiments and calculate sigma naught x as well as K1 and take that value of K1 as representative for the problem on hand. But people also have looked at it, this interpretation, in many different ways. If you look at the derivation from Westergaard's approach for the mode 1 problem, whatever the solution that we have got was for a biaxial stress field solution. It is not for a uniaxial stress field. If you look at Irwin's modification, this could be considered as a modification for a uniaxial stress field, because this minus sigma will go to at infinity cancel with the sigma in the biaxial load. So, people thought Irwin's modification could be taken as a uniaxial case representative solution, but there are also other arguments. See, if you look at really at the crack tip, the value of sigma x is very high. So, near the crack tip sigma x minus whatever the sigma would still be very small. So, there has been discussion in the literature how to take the solution for uniaxial stress field. If you really look at the development, when you looked at what is K1, we said for a biaxial loading situation sigma root pi a. So, we have an analytical expression on what is the value of K1. Now, the question is, this is derived for a biaxial situation, can I use it for uniaxial situation? This kind of question comes. So, what people have done is, for finite body problem, people developed boundary collocation solution and obtained expression which had a factor a by w, a function in terms of a by w, which is represented as beta. So, beta sigma root of pi a. That way you can handle finite body problems. Okay. So, what you will have to keep in mind is, in the near vicinity of the crack tip, the basic solution of Westergaard is still very useful. And what is the other thing that you get when R tends to the crack tip? We will look at what happens along the line theta equal to 0, that is the crack axis. So, what I get here, these terms go to 0, I get sigma x and sigma y both behave in this manner. You have sigma x equal to sigma y in the near vicinity of the crack tip, and later on when we are going to look at what is the size of the plastic zone, I had already given a problem in your review of solid mechanics. Find out the level of stresses when you have sigma x equal to sigma y. in plane stress as well as plane strain. That comes from what happens near the crack tip. The Westergaard solution gives you near the crack tip, at the crack tip both sigma x and sigma y are like this, they asymptotically increase to infinity and goes to 0 when you go along the x direction. But what would really happen to the crack tip? The crack tip is not going to be sharp. In a real material, crack tip would blunt. So, people also looked at solution from a different perspective. This was done by Krieger and Paris in 1967, who tried to find out the stress field when you have a blunted crack tip. How does the solution change? You had this Westergaard part of the solution, plus you have k1 by root of 2 pi r rho by 2 r multiplied by minus cos 3 theta by 2 cos 3 theta by 2 minus sin 3 theta by 2. What is the difference between the two? In the earlier case, crack tip was very sharp. In the second case, the crack tip is blunt. So, when the crack tip is blunt, what would happen to the sigma x stress component? It has to go to 0 because it becomes a free surface. When it is a sharp point, the story is different. And when you look at the Krieger solution, what they have done is they have considered this as a root radius rho, and the crack tip is taken as a distance rho by 2 from the edge of the crack. This is how the measurements are done. So, if I have to find out what happens at the crack tip, I have to substitute the value of rho by 2. So, when I substitute the value at theta equal to 0 and r equal to rho by 2, I get a solution which is understandable from your common sense. You get a solution where sigma x equal to 0 and you also get sigma y becoming a finite value. It is not infinity anymore. Ever since Inglis pointed out cracks are very dangerous, several scientists have contributed in understanding what happens at the crack tip. So, the solution by Krieger is quite useful. The important aspect here is you have this as blunt, and this blunting is accounted for by taking a root radius rho. And if you look at the stress field, it would be something like this. You have a blunted crack tip here, shown as sharp, but imagine that it is a blunted crack tip, and I have some variation of sigma x like this, it is 0 at the crack tip, and the sigma y and sigma x are different, and sigma x reaches a maximum value at a short distance away, and this is nothing but the Krieger solution that I have shown earlier. So, the focus here is you are getting a sigma x value 0 at the blunted crack tip, and sigma x reaches a maximum at short distances away, and your sigma y value is not infinity, but it is very large, but it is a finite value. Now, what we will look at is we will go and find out the displacement field. We would still use the Westergaard solution itself. From the Westergaard methodology, you may not be able to get it for a uniaxial loading situation, but we have seen whatever the final solution you get is reasonably good enough to represent the crack tip behavior quite well. So, we go to the displacement field, and here again what we will do is we will develop it based on the stress function themselves. And what is done here is, since we are focusing on mode 1, the stress function given by Westergaard is represented as capital Z1 and Z1 prime and so on. In the earlier discussion we had kept it as capital Z, because Westergaard used that basic solution to get the stress field for a variety of problems. Now we are going to focus on mode 1, mode 2 and mode 3. In order to distinguish the relevant Westergaard stress function, we would represent them as Z1, Z2 and Z3 as the case may be. So here we are having this capital Z1, and what is the advantage? By taking Z1 in this fashion, the reference axis would be the center of the crack tip, origin of the reference axis would be the center of the crack tip. If I modify the Z, you could also see what happens at the crack tip. In fact, when I want to get the displacement field, I would like to get the displacement field with crack center as the origin as well as crack tip as the origin. I would use them in appropriate manner when I want to understand the concepts in fracture mechanics. One of the interest is we want to see under given loading how the crack opens up. For that, finding out the displacement field with crack center as the origin is useful, and we would develop it for plane stress as well as plane strain. So in the case of a stress formulation, we get the stresses first. From stresses we will get the strain components. The stress strain relationship for plane stress is given as follows, and you have to be very careful in putting the appropriate stress quantities. So epsilon xx equal to 1 by E into sigma xx minus nu times sigma yy. Similarly, you can write for epsilon yy as well as epsilon xy. So in the case of stress formulation, we get the stresses first, using stress strain relationship evaluate the strains, and the strains are related to displacement quantities. So from strains we will have to find out the displacement, and we know from your solid mechanics that epsilon xx is nothing but dou u by dou x, and epsilon yy is nothing but dou v by dou y, and your epsilon xy is 1/2 of dou u by dou y plus dou v by dou x. And what we have done now is, from the stress strain relationship we have written the strain quantities. So epsilon xx turns out to be 1 by Young's modulus multiplied by real part of Z1 minus y imaginary part of Z1 prime, minus of nu times real part of Z1 plus y imaginary part of Z1 prime, and epsilon yy is very similar. There is a change in the sign here and there is a change in the sign here, otherwise the basic expressions look very similar. And I have this shear strain in which we have replaced the value of G in this manner. We know E equal to 2G into 1 plus nu. So that is substituted, and we have written it in terms of E here, minus 1 of 1 plus nu divided by Young's modulus y real part of Z1 prime. See, finding out the displacement from strain is not a simple task, you have to be very careful. If I have only dou u by dou x and dou v by dou y, there is no other interrelationship, then the methodology is straightforward. I can directly integrate expression 1 and expression 2 and say this is the displacement field. What I have here is, I have an expression for dou u by dou x, I have an expression for dou v by dou y, I also have an expression interrelationship between them, dou u by dou y plus dou v by dou x is given as epsilon xy. So whatever the solution for u and v I get, this equation also to be satisfied, that is to be taken care of in your mathematics. Now what we will do is, instead of keeping this as Young's modulus, we will replace it in terms of g, that is what we are going to do it in the next slide, and group the terms. So, what you have here is dou u by dou x equal to 1 by 2 times g of 1 minus nu divided by 1 plus nu multiplied by real part of z1 minus y imaginary part of z1 prime. Then you have expression for dou v by dou y. So, these are carefully grouped, so that you have the Westergaard stress function terms are grouped together. I have this as 1 by 2 g into 1 minus nu divided by 1 plus nu of real part of z1 plus y imaginary part of z1 prime. We will still retain this as z1 and carry on with the calculation. Finally, we would look at one set of solution with crack tip as origin, another set of solution with crack center as the origin. We will get the expressions in terms of r and theta. Until then, we will just keep them as capital Z itself. So, on integration, the expression for u and v turns out like this. These are long expressions, please take some time to write them. So, I have u equal to 1 by 2 g multiplied by 1 minus nu divided by 1 plus nu real part of z1 bar minus y imaginary part of z1, and I have added a function here. Now, this is what you will have to keep in mind. We have the expression dou u by dou x. So, when I get an integration of that, I will have an integration constant. That integration constant is actually a function of y when I have the original expression in terms of dou u by dou x. As far as integration with respect to x is concerned, this behaves like a constant. So, when I go to dou v by dou y, when I integrate, I get a integration constant as function of x. So, I have v equal to 1 by 2 g of 2 by 1 plus nu multiplied by imaginary part of z1 bar minus y real part of z1. So, keep track of when I do it with respect to y, there is a flip over in the functions as well as the sign change. This you have to look at the Cauchy-Riemann condition and make your understanding clear. So, the solution of u and v would be complete only if I also evaluate what are f y and g x. If I know these two, then I can get the expression for u and v, and that is what is summarized here. F function of y is the constant of integration, which can be a function of y only. Similarly, g x is a function of x only. And I have made a statement that for fracture problems, function of y and g of x can be equated to 0 without losing generality. That makes our life simple, but what we will do is we would really go and find out what is the reason behind it. So, for that I need to look at what will happen to this expression, because we had seen we also have interrelationship between displacements in the form of your epsilon x y. So, I will have to evaluate 1/2 of dou u by dou y plus dou v by dou x. We have already got the expression for u and v in terms of the integration constants, which are actually functions of y and g of x. I am not doing that detailed. So, go back into your room and then check it. So, when I do that, I get this equal to 0. So, this you will have to substitute it, and then I would like you to verify it in your rooms. So, dou of f of y divided by dou y plus dou of g of x divided by dou x equal to 0. This is what you get when you substitute it, and this can be rearranged as dou of f of I divided by dou y equal to minus of dou of g of x divided by dou x equal to a, and a is a constant, and we will investigate what is the influence of this. Suppose I go back and substitute the displacement field, what happens to it? So, when I integrate this, I get f of y equal to a y plus b and g of x equal to minus a x plus c, and these are constants, they are constants of integration. So, now I know what is f of I and g of x. So, when I substitute in the expression for u and v or u x and u y, whichever way you look at it, I would like you to do that as an exercise in your rooms. I get u x as a constant b and u y as another constant c. And our solution will not be affected if I take, without losing generality, these be set to 0. You know, in your normal theory of elasticity, though you have solved problems based on stress formulation, only for a very few cases probably would have gone ahead and evaluated the strain as well as the displacement. If you had done that exercise, here also the exercise is similar. And now we look at what is rotation. The rotation is given a symbol omega, that is nothing but 1/2 of dou u by dou y minus dou v by dou x. So, the contribution of function f and g towards rigid body rotation is what you are getting it here. Omega equal to 1/2 of a plus a, which reduces to a constant a. A corresponds to rigid body rotation of the component and may be set to 0 without losing generality. So, what we are actually looked at is, we have said when you integrate dou u by dou x, I would have an integration constant appearing as a function of y. When I integrate dou v by dou y, I would have an integration constant appearing as function of x, which is g x, without losing generality. By a detailed analysis, it shows they represent only rigid body translation and rotation, we could make them. So, the displacement field is finally obtained in this fashion. U is given as 1 by 2 g of 1 minus nu divided by 1 plus nu multiplied by real part of z1 bar minus y imaginary part of z1, and v is given as 1 by 2 g of 2 by 1 plus nu imaginary part of z1 bar minus y real part of z1. You know, our interest is to get the displacement field with crack center as the origin as well as crack tip as the origin. So, for crack center as the origin, use the stress function as z1 equal to sigma z divided by root of z squared minus a squared. For crack tip as the origin, use z1 equal to k1 by root of 2 pi z naught. This I would be emphasizing it, because when you take up a book, they give an expression, you may not know unless it is very clearly said whether those expressions are related to crack center or crack tip. This you have to keep in mind, and also whether it is related to plane stress or plane strain. Now, let us move on to finding out the displacement field in the case of plane strain. And you all know the stress strain relations, these are written here for convenience. Epsilon x x equal to 1 minus nu squared divided by Young's modulus E multiplied by sigma x x minus nu by 1 minus nu sigma y y. Epsilon y y equal to 1 minus nu squared divided by Young's modulus multiplied by sigma y y minus nu times 1 minus nu sigma x x. And if you really look at these two expressions, can you get them from your plane stress case by making some modification to Young's modulus and Poisson ratio? In fact, you can do that. If you look at that expression, instead of Young's modulus, you take it as E by 1 minus nu squared. Instead of Poisson ratio nu, you put it as nu by 1 minus nu. You will get from plane stress to plane strain. And to save space in books, they might give one expression and say substitute it in this fashion, get it for plane strain. This is very common in elasticity books. And our epsilon x y is given as 1 plus nu divided by Young's modulus into tau x y. So, I can substitute these stress components in the basic equation. So, I get strain quantities related to the Westergaard stress function as follows. It is quite long, please take some time to write this up. So, I get epsilon x x equal to 1 minus nu squared divided by Young's modulus multiplied by real part of z1 minus y imaginary part of z1 prime minus nu by 1 minus nu real part of z1 plus y imaginary part of z1 prime. Then I also look at what is epsilon y by, which is 1 minus nu squared divided by Young's modulus into real part of z1 plus y imaginary part of z1 prime minus nu by 1 minus nu real part of z1 minus y imaginary part of z1 prime. So, what we will do is we will group the terms involving z1 and z1 prime and get the expressions, because that will make our life simple later. So, I get dou u x by dou x equal to 1 minus nu squared by Young's modulus 1 minus nu by 1 minus nu multiplied by real part of z1 minus 1 plus nu by 1 minus nu y imaginary part of z1 prime. Then epsilon y y equal to dou u y divided by dou y equal to 1 minus nu squared by E multiplied by 1 minus nu by 1 minus nu real part of z1 plus 1 plus nu by 1 minus nu y imaginary part of z1 prime. See, the expressions are long, I do not expect you to remember, but nevertheless your notes should have these expressions. In fact, for your examination I would allow you 2 sides of an A4 size sheet where you could have the formulae you think that are relevant can be written and come, because in a course like this you will have to encounter long expressions, there is no other go. It is not a test for your memory, but you need to have those equations, and I have been emphasizing whether these equations are referred with respect to the crack tip or crack center, make those notes also appropriately, and you will have a good set of equations summarized in your notes. And while developing the plane stress situation, we have looked at the integration constants can go to 0. So, we take advantage of that understanding. I integrate the expressions for strains and get the displacement u as 1 by 2 g into 1 minus 2 nu multiplied by real part of z1 bar minus y imaginary part of z1. Can you now go to your plane stress expression for u? Can you get from plane stress expression for u to plane strain expression for u? I have to make some small changes in the Poisson ratio. If you substitute nu by 1 minus nu in the plane stress equation, you will get the equation that you have got in plane strain. And we have the displacement component V as 1 by 2 g 2 into 1 minus nu imaginary part of Z1 bar minus y real part of Z1. And here again it is emphasized, since the expressions are still in terms of the stress function, also make a sketch, because this is very illustrative. You are taking crack tip as the origin and the relevant stress function is given as Z1 equal to K1 by root of 2 pi Z naught. And here you have crack center is referred as origin, and Z1 is given as sigma z divided by root of z squared minus a squared. So, I can get referred with respect to the center using this stress function, referred with respect to the tip with this stress function. So, essentially I will have to know, if I have to find out in terms of r and theta, I will have to know what is Z1 and what is Z1 bar. This is what I will have to do. And this is just to verify your notes, it is all summarized here. In this slide you have the expression for plane stress as well as for plane strain, the displacement field. If you have made any typographical errors, please verify and correct them by looking at this. See, now I am going to qualify the displacement field which is very close to the crack tip, because I am going to use the stress function Z1 as K1 by root of 2 pi Z naught. The moment I bring in this, you have to understand it is a very near tip field equation. In this case, it happens to be displacement field, and you have already seen how to write it in terms of cos and theta. So, Z1 is nothing but K1 by root of 2 pi r cos theta by 2 minus I sin theta by 2. While developing the stress field equation, you had come across this simplification. In the stress field equation, we were worrying about Z1 and Z1 prime, and here we are going to worry about Z1 and Z1 bar. So, I have this expression. So, when I have to find out what is Z1 bar, that is nothing but 2 by pi whole power half K1 root of Z naught, and this could be written in terms of 2 r power half divided by pi into K1 into cos theta by 2 plus I sin theta by 2. So, now I have the expression of Z1 as well as Z1 bar in terms of r and theta. So, I can substitute it in the expression and get the displacement field in terms of r and theta, as simple as that. And what is written here is, I have the expressions for both the plane stress as well as plane strain. In order to make your understanding very clear, the diagram re-emphasizes that whatever the solution you see for the displacement field is referred to crack tip as the origin. So, the plane stress case, I have the expression for u displacement which is given as ux, v displacement which is represented as uy, and W displacement is represented as u z. This is very important, you should not forget this. We will look at each one of them. So, u x is given as k 1 by g root of r by 2 pi cos theta by 2 into 1 minus nu divided by 1 plus nu plus sin squared theta by 2, and u y equal to k 1 by g root of r by 2 pi sin theta by 2 multiplied by 2 by 1 plus nu minus cos squared theta by 2. And when I come to u z, I have this as minus of 2 nu divided by e into k 1 root of r by 2 pi cos theta by 2 multiplied by b. I had mentioned near the vicinity of the crack tip, because of very high stress values, you would find a lateral contraction. In fact, we saw that as a dimple, and now what you have is you have an expression for that displacement itself. In a normal problem, the displacement would be quite small. Because you have a crack problem, I have the value of k, and if you look at the parameters close to the crack tip, you find that this value is quite significant, you cannot ignore it. And if b is the model thickness, you will have to multiply this by b to get the u z displacement. So, if I have to get this expression, I can simply substitute nu as nu by 1 minus nu in this and get this expression also. Take your time to write this down. So, this gives you very near tip displacement field equations for the case of plane stress as well as plane strain. What is striking when you compare the displacement field with the stress field? You have the expressions before you, and we had seen in the case of stress field, the stresses go to very high values when you go very close to the crack tip. In practical materials, it cannot go very high, it has to reach the yield strength or whatever the work hardening phenomena that takes place. So, the stress values will still be finite, but very high. When you look at a displacement field, can you have very high displacement at the crack tip? You cannot. So, there is no singularity attached. When r goes to 0, what happens to these displacement components? The displacement components also go to 0. See, this is another check for you to ensure that you are in the right direction. Your method of mathematics employed has been consistent. We got singular solution for the case of a stress field, we got a bounded solution in the case of displacement. And books give these expressions in various forms. It is desirable that you have the expressions available in all the possible ways. Books also give you expressions combined for plane stress and plane strain. You can write them down. U x is given as k 1 by 2 g root of r by 2 pi cos theta by 2 multiplied by, this is not k, it is to be understood as kappa, kappa minus 1 plus 2 sin squared theta by 2. Then you have u y equal to k 1 by 2 g root of r by 2 pi sin theta by 2 multiplied by kappa plus 1 minus 2 cos squared theta by 2, where kappa is defined as 3 minus nu divided by 1 plus nu for plane stress. It is given as 3 minus 4 nu for plane strain, and g is the shear modulus. So, when you look at expressions like this, you should understand such expressions we have seen in the class. This is nothing but representing the displacement field in a convenient form, essentially to save pages, that is what people have thought about it. but expressions are given differently in different books. So, you should know how to look at them, and mind you here for the plane stress situation u z is not given. So, you have to know for the plane stress you also have u z, and you know these expressions are verified several times to check for any typographical error. Nevertheless, I would request you to check for any clerical error in any one of these equations, and you will have to filter out what expressions are important from your examination point of view. That is a different exercise, fine, because I do not expect you to remember, but you should know what is important and what is not important. That judgment you will have to make, that itself is an understanding. Okay. See, one of the things that I have been mentioning in earlier classes was, when the crack opens, it opens like an ellipse. This is what I have been mentioning it. You know, when I make a statement like this, once you have got the displacement field, you know, you will also have to evaluate it and qualify it and reconvince ourselves, yes, the crack opens indeed like an ellipse. So, we have to look at that, and we already have the expression for Z1, and when I want to do this, I want to look at crack center as the origin, crack center as the origin. So, I have taken Z1 equal to sigma z divided by root of z squared minus a squared. And what happens to Z1 bar? Simple integration. I get this as sigma z root of sigma z multiplied by dz divided by root of z squared minus a squared. And what is this displacement? This is nothing but the y displacement. So, I have to look at the expression for uy, and that is given as 1 by 2 g multiplied by 2 by 1 plus nu imaginary part of z1 bar minus y real part of z1. In fact, you are going to find out the displacement for the case when y equal to 0, because that is what defining the crack. So, you really want to know for y equal to 0 what is the expression for the displacement. And when you look at here, this simply reduces, because when you substitute y equal to 0, this term knocks off. So, essentially you will have to calculate what is the imaginary part of z1 bar, and z1 bar is given in this fashion. Now, you have to go and integrate this equation and find out what is the final expression you get. In fact, for the next 2-3 classes, you know, I would appreciate that you go and refer the table of integrals, and also when you have functions with square root in the numerator or denominator, we will have substitution of variable and then do it. Look at those steps also. So, take your time to look at the table of integrals. So, that would help you to do the integration in the class and verify your solution with mine, and finally arrive at the relevant equations that are of interest. So, in this class what we had seen was, initially we looked at Arvind's modification of Westergaard's stress field. There we had seen his modification was very simple, at the same time very significant to model the fringes seen in an actual experiment. So, from an experimental point of view, you will evaluate k1 as well as sigma naught x, and you will take that value of k1 for all your fracture calculation. And I also mentioned there was a debate in the literature how to use Westergaard solution for uniaxial loaded situation. People have said one could think of Arvind's modification as the candidate, but nevertheless in a later class, since all bodies are finite, we will look at how to find out the stress intensity factor for finite body problems. For an infinite body with a biaxial loading, it turned out to be k1 equal to sigma root pi a. The basic structure would still remain same, but we would have additional factors. And we have also looked at, for the case of blunted crack tip, how does the stress field changes. You cannot have sigma x at the crack tip, it has to be 0, and you will also have a finite value of sigma y. This was done by Krieger and Paris. Then later on we moved on to looking at the displacement field. We retained in terms of stress function, so that we could get the solution with crack center as the origin or crack tip as the origin. We have actually got the expressions with crack tip as the origin. We have looked at it for the plane stress case, plane strain case, and also we looked at how to combine these kind of expressions and see as one expression, and we also emphasized the role of the displacement UZ component in the case of plane stress.